the maximum function. The distribution function in the source. Ah, it's almost lunch. It's lunchtime. Oh.
Yeah.
Okay, but I'll finish because this is our minute ends after this. So we can turn on and off the preservation of the Maxwell distribution function per species. Maybe we don't want to hit this preservation of energy function for some species, but we want some other species. So we activate it in the source once, in the source section here, but we can disable it per species. We cannot enable per species if this is 0 here. So if you want to have it anywhere, you put it here 1 and then disable it per species if you want it. If you put per species 1 and here 0, it will not be activated for any of the species. So how do we load initial plasma? We can put initial density, and it's the only time we have information about the density a priori. If we load it from the beginning with a given density, a given temperature in the parallel direction and the perpendicular direction, they're usually the same number. Or we can inject from the left wall or from the right wall, but injection is a source. So it's particle, which is 1 particle per second per square meter. So you know the area in square meter. It's in the beginning of the file. Here is the area. Yeah. You know the time step, how much, and then from this you calculate yourself how much this value should be, because this is in SI units. This particle per, this is the physical value, like an experiment. Particle per second per square meter. And again, with a given temperature, we can put a drift in the positive drift in the left means it goes into the simulation. If you put a negative drift, it goes out of the simulation. You're not injecting it. If this is negative, you're not injecting the particle. Yeah, and this is a Z component if you want a drift. Injection type. This is in the it's 0. It's in the some quantum stuff. I don't know. And from the right wall again, flux, temperatures. I made a tutorial with this initial M. Now the source strength, you have it there as particle per second per cubic meter. If you want to adjust the source for a particular species, then you put this con S. This is I forgot what con comes from. It goes from 0 to 1, and you can shorten the source strength or maybe increase it. Yeah. So 1 means is the same value as in the source section of the input file, which is this one here. Yeah, dn over dt. This is you multiply by this and you modify the source for this species. And of course, because it's a source, you have to give it a temperature in a parallel and perpendicular, and also drift you can give. You see that there's another line with the same information. This is for source 1. So this is for source 0, the first line, and the second line is for source 1. What is very important here? This temperature here in species 0, no, actually, no, the temperature in this line actually is the temperature used for the heat routine, which means to preserve the distribution function of the electrons in the source. The electron will collide with another imaginary electron of this energy here, 5. So this value here, so if you have heat 1 and this value here, remember that no matter where you inject, no matter how you put them, if you have a source region with heat 1, your particles will be heat up or cool down with this value here. So in one of my simulations, I made a mistake where I was injecting with 50 electron volt, and this value here was 10. Because I was not using source 0, I was using source 1. So you see here in source 1, you can put hotter, but because I had heat 1 here and in the source region as well, then my particles were being cooled down. Not all of them, but there are collisions, there's probability, yeah, to this value. So I was cooling down my electrons in the source. It was a rookie mistake. You can have diffusion, so your particles can disappear from the simulation. This is the diffusion coefficient. It's in the input file. It tells you which is the pair, the ambipolar pair of it. It's the ion. If an ion disappears, only one electron disappears with it. For diagnostics of energy distribution function and velocity distribution function, you have to give how many bins in the energy range or velocity range. And it's done here. This bin is used for all species, if I remember correctly, because of array, because of memory allocation. But the value min and max, the minimum and maximum values of energies that we will look into. And for velocities, the same. So min and max is the same for all the species, but for velocities is different. If you want to have recycling of species, electrons will touch the wall, they'll disappear. So recycling is secondary 0 here. If you want to have electron emission from the wall by electron bombardment, this should be 1 or 2, how many extra electrons will come out from the wall because this electron hit the wall. And if you hit the number and he put the species, type 1. So if I put here 1 and 1 means 1 electron hits the wall and extra electron gets injected with the temperature expressed here, with the energy expressed here. If I go to the ions, of course, charge is 1, not -1, but 1. Come on. Is 1. The mass of the ion, we can put here relative time 20 because it's much slower. You can give the energy in the source again, but if I go to the recycling, surface physics, so this ion, when it hits the wall, will become a neutral. Why? Because it's species 3 here. You can have another species coming out if you want, but actually, if it's recycling, this is ignored. So only the first number is being taken into account. It becomes a neutral with the energy of 2 EVs here specified. So this is called ion recycling at the wall and becomes a neutral. Okay, this is the input file. I don't know what time the canteen closes today because it's Friday.
When you have the steady state, for example, this input file.
Yeah.
And after that, if I want to change the magnetic field, for example, I start again by 0 empty space, or I can just rerun the same dump file.
Of course, the sheath will so the sheath will form also with the magnetic field angle,
okay,
because it's its magnetic pre-sheath changes I don't know. I don't know what's the best way. Probably depends. If your simulation, if you waited 2 months,
Better.
probably
At least,
better. I don't know. I don't know which one is better. This has to be. I mean, David has some experience with it. I have some experience with it, but because I'm doing time dependent,
Yeah.
in my case, it will scramble some things for me. But if it's constant source, then this I don't know. Of course, there will be, let's say, a shock to the system because something changed. There will be a potential perturbation, but probably it will flatten out this perturbation and then it will reach something. Of course, plasma is long-range interaction, so a perturbation here will affect everything and everything will move. So you don't have to wait much time actually to relax. But I cannot guarantee that this is equivalent to a fresh start. I don't know how much actually did change. I don't have such quantization. If the canteen is closed, we can go to Zbornica and have a burger. I recommend the place. So I want to spend maybe 5 more minutes and that's it. I want to make some run. So I prepared a script for our cluster, which is load MPI to use the MPI threads, and then use MPI run 8 threads, bit 1 with this training input file, which you just seen before. So because I noticed now a mistake when I explain to you, I'll open this training input file and change the column collision. Where is it? Here's one. Say it should it's always read as a float, but I just put maybe let's put into the just for fun to have something here. Okay, so now I open terminal. And I run this shell script, which is actually MPI run. Yeah. So this I'm going to run now. So here. This. Okay. I moved the input file, but actually it needs. Okay. Okay. I know what I did. So I will go to the location of the input file. So I am in. So this is the repository and this is the source. Okay. He doesn't find the collision files, the files for collisions, because okay. It should be like 15 seconds. I don't remember what I activated. Okay. But here it says primary job exited normally. Primary job terminated normally, but one process. But anyway, this is good. If I look here, what I see, dump files, of course, and this .n files. Now I want to see these .n files. I have a script which I prepared. This I will upload to the bit1 repository so everybody can use them. It's called training.py, yeah? So what it does, it calls this. So I want to plot this .n files. So this I put to false, this I put to false, yeah? And I'm going to run this script. So I use Python training Okay, it doesn't know training.py. Not here. Where did I may save it somewhere else? Okay. I think it's in here. Python training.py. Okay. Okay, now what's wrong with it? It was working yesterday. Let me check. So import matplotlib. Module. Okay, maybe I'll just use this. Where is training? Okay, I'll just use it from here. Training. Okay, this file. Yeah. So what I'm going to do, I'm going to get the data and plot it. So I'm going to run this. So what happened during this simulation? My particles started from here. So NE is number of particles per cell, averaged. It's not a total, but this is just for me to see how many particles per cell I have in the simulation, not to reach this upper limit, which I put 1000. Yeah. So what happens is NE is electrons, ions, and neutrals. And N, so the number of electrons, of ions, and neutrals per averaged, let's say, per cell, but it's in time. So you see here on the x-axis some records. So what we see is that, and these are 3 locations, at mid-plane, which is somewhere in the middle, at the outer diverter, the outer wall and inner wall. So what we see that, and what did we simulate? We simulated, if we go into the input file, we simulated initial injection. So here, initial 20, 10 to the 20 for electrons, for ions, and nothing for neutrals. So we don't inject neutrals, yeah, let's say, for this case. And what we see that the number of electrons drops down at the wall. Why? Because they fly around, they touch the wall, they disappear. The number goes down, but in the middle of the simulation, which is the blue one, is roughly, it doesn't see actually the, in the middle of simulation, we still have electrons, yeah, they're flying around. For ions, the same, they go down at the wall, but the neutrals at the walls goes up because these ions, when they go out of the wall, they become neutrals. That's how the neutrals goes up. But this is average per cell, so we see less than 1. So the number that exists divided by all number of cells. So that's why we see here. So this is a way to see what happens in your simulation in time. This is the minimum that you get from bit 1. What happens at different locations. So how did they choose these locations?
This is the ionization test, right? Which test is this one?
Yeah, ionization, but that doesn't matter because we don't have neutrals to ionize anyway. So
Yeah,
the ionization doesn't take place because these neutrals, they just barely appear.
okay.
So so we just put them initially and we don't inject, we don't have a source for this. Yeah. So if we go to the input file and we see what actually we activated for diagnostics, see movie flag is 0, so we don't have that, and slow is 0. So this is the fastest way. Now we put slow equal 1. Yeah. And now we see here we have what files? We have .n files, yeah? And the dump are always there because it saves at the end. .n. Now I run the simulation again with slow equal 1. No. Take another 15 seconds. How do I make this text bigger? In large font. Oh, this is a very annoying way of, okay. Font, large font. Okay, now we're getting to font, large. Okay. It takes a bit longer. Okay, it's finished. Primary job table normally. Okay, this is okay. Now we look here what files are. Okay, it's not very okay. I'll just enlarge it more. So besides the .n that we had before here, .n that we saw the plot before, and the dump files that the autoliner makes when we put the dump step in the input file. Now we have Coulomb collisions, which tells us which species suffered Coulomb collisions. We have some flux, some heat flux, but what I'm interested in is in .t. So this .t, I open one of it, now contains macroscopic quantities, like, but it's full of values like density, temperature. So this is, for example, density. This is this is Vx, Vy, Vz in the cell, per cell. So this is macroscopic quantities per cell. So average, like the fluid quantities, yeah, Vx, Vy, Vz. The density in the cell, the temperature in the cell for electrons. And then it repeats for ions. It goes for ions, and then it goes for neutrals. And then it fills up all of this line. This is one full line. Yeah, this is explained in the manual. Now I want to see what I plotted here. So I go to my script and I want to plot. I didn't prepare. Okay, what I'll show you is the movie files, which is the same information as in that file, the same information as here, but for each time step. So I will go and go in the input file, leave slow equal 1. I'm not sure if I think it works also slow equals 0, maybe the movie flag or not. But anyway, so I have 1000 time steps. I want to average every 100 steps. Okay, so I have maybe 10 records of the movie, yeah? I don't think this works with 0 here. So I always put a number different than 0. So maybe write this somewhere that you know that movie step. I've never tried it. I think I tried it once, but I'm not sure what was the outcome. Because you have to check the data to see if it looks good or not. That this movie step should not be 0 if the MV flag is not 0. Because he counts how many steps after this should I skip before starting again the averaging every 100. I'm not interested in energy flux type diagnostics for now. So I will now save this. Yeah, run again. And when I will list the files, you will see that it will have movie files now. For each MPI rank, of course. So it's a bit, let's say, annoying that each rank creates a number of files, so you'll end up with many files. Okay, it terminated normally, it says here. And now if I list, now I see I have movie files. This here. And movie files is the same as that files, but now each time step it's being appended in the same movie. So if I look in it, it's way longer because it's the system in time now. So now I want to plot it. So I go here. This I don't want to see anymore. I want to see this. So now what the script will do, it will join the movie data from all CPUs. And it will show me the whole system. So you'll see some plot, some potential. So on the bottom you see time in milliseconds. Okay, this is because we only let it run 1,000 time steps times dt, which is 10 to minus 13 seconds. That's 10 to minus 10 seconds of simulation time. So this is what you see here. I will go each down. So first electrons, what I see, because I uniformly injected them in the system, they are uniformly distributed. And you see here the density 10 to the 20. And you see a bit of fluctuations because it's particle in a cell. You know, it moves around these particles, yeah? And this is the temperature. We said 5 eV, it's more or less 5 with a certain error, but it's 5 eV, yeah? We want to see the sheath. Well, we have to zoom in at the wall. You see there's something here. I limited my data actually to 2,000 points so that not use the all 10,000 that was in the input file, 10,000 cells. So here on the X coordinate, I don't use 10,000, I use only 2,000 just because my screen doesn't have 10,000 pixels anyway. So it makes no sense. But okay, if you want to zoom in, then you have to. This value can be changed in the script. Here, this should be the sheath, but because I'm lacking resolution, I don't see it in this data, but it's there. The electron temperature, and then ion. Disappeared again. Ion density. The same ion temperature. So this is in space, yeah. So this is 0 is inner wall. This is outer wall. It should be this the distance, but I think I use short or something. I have to check why is not doesn't what doesn't show here. Okay, this is in time. What else can I see? Potential. Neutrals. There's no neutrals in the system. You see, I put my mouse here and the value that shows here, and this corner is 0 because there's nothing in the coordinate. But if I go to the wall where my ions now should become neutrals because they touch the wall, you see it's building up from nothing. It goes to this value here. Yeah, it goes up. The number of neutrals at the wall goes up in time. The time is this axis. So with movie files, you can actually see how it's evolving. This is one way of representation. You can have 3D set of color map. Okay, and a potential map. It's fluctuating because it's short, didn't stabilize. My particles are disappearing from the system without injecting new ones to screen. And okay, so this was for movie files. Now, if I want to measure the distribution function of a species somewhere in the system, then I go to this N-Dike point. I want from here to here, I want to see the distributions of all particles per species. But here is the whole simulation domain. So now I'm going to see the distribution through the whole system. I put here 2, then I put here 2, then I copy this line here and I put, but this should end somewhere closer, and the next one should be the same or greater, than the next one. So now I have 2 regions. I measure this and this, but now it's equivalent as the one before. But let's say if I want to have narrow at the wall, I put here, let's say 299. And now I have close the wall, first wall, the left wall and the right wall. Yeah. Only this I want to measure the electrons. But because this was already here, I thought I disabled it, but I didn't. But I already have the data, so I just run it. How I know? Because if I look here, should have it is not. PDF file. Why it is not here? Okay, let me check the input file. Maybe I missed something to activate. Not here. It's here. Input file. So I will remove this again. Let me just. And back. Maybe this NFFT, slow 1, 24, E24. Okay, let me put here 25. Maybe needs one more step. Remember. Or maybe it's this. I don't remember. It's maybe. No, it's something else actually. No, we don't need this. So if I put a C here, I transform this line from float to string. So when the code reads the input file, it will ignore this line, that I can reuse it later. Otherwise, you have to remove it completely. because he will wait. He wants to read 3 values, but he only finds 1 and then he stops. And then the code hangs indefinitely, and you don't know if it's running or not. So what? And I'm going to do this. I'm going to put a message at the end when he reads the input file to say, input file read successfully, and now you know that he has started computation. If you don't read it, if you don't see this message in the output of the code, then you know something is wrong with the input file. So I will put this, yeah. Okay. So diagnostic points is here. Okay, why don't have the files? I'm now why the files are not here? Actually. Okay, I will see. This is that is annoying actually. Was this here already? Before it was, yeah?
That was how it was, but you haven't changed
Yeah.
the number of time steps. I think you might.
It should be slow equal 1.
You change like how many total steps you need.
Yeah, okay.
Meaning to-
I'll just rerun. So you'll see that I'm always starting from empty simulation. If I want to continue, I need to put here where it saved the dump file and save it in this. It's the same name of the file, but with dump extension. Now, if I save this and run, actually will continue from this state. If you don't put this, it will always start from 0.
All the time steps, like the amount of physical time that's passed, be like updated if you restarted from.
No, so every restart starts from time equals 0.
Okay.
This information, it can be saved in the files that you are saving as output.
Okay, all the files are rewritten if you don't put this extra step.
No, this is to actually read the dump file and to
Yeah,
continue
but
from
I
there.
mean, it said it starts by the time zero, right?
Yeah.
So that's all all data to be written.
No, because data has already been saved. So you have.
But then isn't it going to output like the same names file?
So some files will anyway be, some files like dot files, they are overwritten every dot steps.
Yeah.
Anyway, even if it's a new simulation, it's the same simulation on another. Movie files will be appended if they exist. From the previous simulations, they will be appended from the new simulation. So files which are appended during one simulation, they are usually appended also with the next.
Yeah, without.
Yeah. So if you want to restart a simulation from a checkpoint, you need to also revert this information from that checkpoint so that it's appended to it, so that you don't append with a bad simulation in the meantime. So you have good files, then bad simulation, and good files again. This has to disappear. So
there's a way to verify that the simulation is good or bad.
After it finished. It doesn't have in-situ visualization. Yeah. So now let's see. Well, blimey, I don't see this dot F, and I don't know why they're not appearing.
The second column at the bottom, but that 0 left. There.
No, this is a flux. I need it's a different and something to do with the input file, and now I cannot. Maybe I'm too blind to see it. MV flag, MV step. Slow equal 1. From here to here. Okay, I just put here just for fun this one, but could it be that it doesn't run where MV flag is activated? I just put here 0. I run it again. I'll see if it was meant like this or not. So now you see, it tells me that it found some dump files and it starts from them. And puts me the time that the previous simulation finished at.
Have you this one was tested or can run on multiple, I would say, pilots? Or it's just PCC?
There are multiple compilers. If you look in the make file, there's a lot of them.
Okay.
Yeah, I can open it for you now.
No, because I'm running it on KMP compiler, it's kind of, doesn't run well. So I'm just wondering if
So you have, okay, MPI CC, but there's from Intel, I think CC. I see. It's not very. I don't know how to make this. But I have an older version of Makefile for multiple machines. So
okay. You talk.
yeah. So this finished. Let's see. No files here. The movie. Okay. No. Okay. 1 more minute I'll spend with this. So NFFT is here. So 1. That file dump step last step. NFFT was 1004. Okay. We flag and we step. This is independent anyway. And this is min max 1. Yeah, I don't know. Because yesterday I managed to do some graphs. I'll quickly look at the manual and look for this TDF. Hmm. So MV flag. So okay. So it depends on MV flag. Okay. Oh, I see. So MV flag. So to have distributions of particles, MV flag should be bigger than N15. Okay, this is not documented. So I'll put MV flag 1024. And now this is more than or equal to N50. And now I think this will give us because it looks like in the input file, it looks like many particles. Okay.
And that condition is only when you have slow one.
Sorry?
Is that condition only when you have slow one?
So slow, yes, only. So in the input file to have the distribution of particles, it says if slow is 0,
Yeah.
no, slow is 1, these are generated anyway, but it depends on this movie flags. But this is averaged over NF50. So NF50 has to be smaller or equal than movie flag, but NF50 has to be a power of 2. MV flag doesn't have to be a power of 2. So I put this 24, and this is movie flag. Where was it? Okay, I'll just run it. But I'll run it. I see that there's an issue with loading, so I'll just run it from the beginning. So I will not use the dump file because I didn't, this was like a fast example. I don't know what's happening in there. Why there's more particles all of a sudden. So I'll run this. And I'll upload these scripts to the repository of Bit1. And after this, we'll finish so showing a plot of this, and then after that, I'll finish the tutorial. And of course, I'm available on email, and yeah, I don't see it. I don't see it. Okay, one more. So all, maybe need to go one step more. Okay, let me put here smaller number. you know, trying some combinations. So movie. Ah, okay. If n50 more than 0 and slow equals 0. Okay, so it seems it's like a weird combination. So move slow is 0, movie flag more than 0, and F50 more than 0. Then I can do this. Okay. Let's see, anything here? No. Okay, so I think this was the, so movie flag more than 0, and F50 more than 0, and slow equals 0. I mean, why this is not printed when slow equal 1, I don't know. But let's see if this is running or not. And this code evolved on the needs of the user. So some things maybe are duplicated in the input file or are not used, or some functionalities require some other combinations. Okay, of course, in the future, the code will be trimmed to be easier to have these outputs. I don't see them. Ah, it's here, TDF. Okay, so we just need slow equals 0. Now we have these files. Again, per MPI rank, everything is per MPI rank. Any type of file is per MPI rank. So now I go to my plotter. I don't want to see movie files because it's constant. Nothing is changing except some particles going out, and I want to plot this. So how this is used? I tell him from which rank I want to read, because I can't make hundreds of plots. I want to give a label where this is maybe inner diverter, mid plane, outer diverter. This ranks, what these ranks are handling, which region of the space, which species I want to plot, because each file contains for all the species. What are the species name? Electrons in this order. 0, 1, 2 is electrons, ions, neutrons. And then I want to run this. And this is it. This column is electrons, this is ions, this is neutrons, and the rows are the 3 regions which I showed. The top is the left wall, which is called inner diverter. This is the mid plane, which is the middle of the simulation. And the last row is the other wall. Or let's say averaged per rank. So the rank 0, last rank, and some middle rank, basically. Not at the wall, but per rank. So on the x-axis is the energy, on the y is in time. So the distribution function time doesn't change much, because but you see that neutrals actually, some neutrals appear here. So you see in the energy at the wall, inner wall and outer wall, there's some strange, and because they're very small amount, they don't form a good distribution. So how to read this is actually, so it's a Maxwellian starting from 0, going up the peak and going down. So it's basically, I will make an annotation. So if you would look, in time, the same x-axis but the y-axis is the f, the value of the distribution, be something like this, peak. So the peak of the color means the peak of the distribution. Yeah, and then it goes like something like this. And this is 0 now, where the blue is. Okay, maybe it's the peak is somewhere. Okay. So electrons for ions and neutrals.
Is there a way of improving the neutral distribution functions other than just having? I mean, I guess you need more neutrals.
Yeah, need more neutrals. Yeah, and then they'll leave the simulation run longer, so that more ions go out, and more neutrals are being generated.
Okay.
But you see here, a broken distribution, more or less. Yeah, okay, this is all. So the idea is that to run bit 1, depending on what you want to simulate, you turn on and off features in the input file. And for diagnostics, the same way. And it takes a lot of time to understand the input file because it has everything in it, for everything, including run and diagnostics. So that's why it's a big file. And for plotting, I already have scripts for almost all the data that bit1 can output. But of course, and I'll put examples on how to use them. And like in this tutorial here. And because without plotting, you do not see what happened. Yeah. Okay. And if you have questions about, let's say, what you want to simulate, like the length of the system, what magnetic field, and how do I create these parameters? Time step, cell size, because they are interconnected. I have a file. I'll just open the file and that's it. And because open file. And I'll also provide this calculating file. So you give values of magnetic field, density that you expect, the length of the system, temperature of electrons that you put in the input file of the ions, of course, mass, angle. It's just a constant anyway. You see, I put here some from some other machines, blah, blah, blah. And then, this repeats. And then we calculate the thermal velocity of electrons, of the ions, the pi length. What?
Which file?
This is a custom file I made to help me create to give me the values for the input file.
So that you can resolve, say, the perfect frequency or the divider.
Yes, so it gives me the time constraint for plasma frequency from cyclotron frequency, and then I print out this. So I take and I calculate the minimum of them, and this will be the time step in my simulation, the minimum of all.
So this is these figures are manually stored in somewhere in simulation, one of the files.
No, this is, I created this script and it takes the values that I put in here.
So this gives you the parameters that you feed into the file.
Yes, so
I see.
yeah,
Okay, so
because if you choose the cell size, so the cell size is length of the system divided by number of cells. So length of the system is an input, number of cells is an input, and from there get the cell size. But also give the temperature, the energy of a particle. But if the particle is too energetic, I mean, if that value you put in the energy multiplied by the time step you put in the input file is more than your cell size, then the particle will jump too much. It has to jump only one cell size. And for example, yes, and I'll say, okay, this will be my time step for the simulation. This will be my number of step of cells in the simulation. And I can use this subcycle for ions from the ratio of the terminal velocities.
And that's where you change the relative time.
Yes. So so you give the length of the system, this Lx, yeah, length of the system, and then you get the number of cells that you can use to simulate your system that you put in input. Of course, if you want the other way around, you want a fixed number of cells. And then you get the time constraints for this new, so the time for the new, so with enforced number of cells, you get this dt, and because if you force the number of cells and you force the number of a system, you force the cell size. And now you have the energy input over particles, and it gives you the new time step you have to put so that. And of course, it's just a custom script. It's good. It helps to fill in the input file. So I'll also put this on the repository. Yeah. So before this, we were doing this by hand. You know, what's my cell size? What's my particle energy? And this, but we don't. This doesn't have to be like this. Yeah. And here you see I limited the time step for one particle is 5 times the thermal velocity, because in bit 1, no particle is going 5 times more than this. It has a cutoff. Okay, that's all.
Thank you.
So how do I share? Oh, did the record stop? Oh no, it didn't. Okay.
You record all the.
Yes. How do I stop the recording?
Is it by the share screen? There's a record button to the right of that. Yeah, and then you can do. I guess you can do it on the screen that's in the room.
So I'll just leave. I'll just leave.
Yeah.
Okay.